Hello everyone, this is the video lecture of section 12.7 part 2 of Calculus 3 Math 2533. Okay, so last time we introduced triple integral of a function of three variables as a limit of triple Riemann sum, first starting with a rectangular box, and then we extended that to general domain, which is there is type 1, 2, 3 in 3D version. It's similar to type 1, type 2 in two-dimensional, double integral, right? Just one more variable. For example, the most typical one is that this is type 1 in 3D. So for given xy in the domain of D, z runs from u1 of xy to u2 of xy. Something like this, your domain. Top surface is z equals u2 of xy. And there will be some, let's say, inside. The bottom surface is z equals u1 of xy. And xy is, this is D, or given xy. It enters through u1 of xy, and then going out, going out of the region through that point, right? So that's type 1, and where D is also type 1 in 2D. If D is type 2 in 2D, then xy will be, reversed. Y equals from C to D, x runs from h1 of x to h2 of h1 of y to h2 of y. And then you can have a type 2, which is in the two-dimensional domain is projection onto the yz plane, and then x runs from u1 of yz to u2 of yz. And type 3 is cylindrical, general cylindrical, region. It's not really a cylinder, but the axis of the region is along the y-axis. So we did those ones. So let's do a few examples. Okay. Now, example 2. As usual, you're supposed to have print of lecture note 12.7. And when you see this, watch this video. Okay, so you might want to write down some more comments as you go along here. So evaluate this over E. Now, this is our f of xy. It's a very, very simple function. Okay? Now, E, where E is, okay, they describe it as bounded by the four planes. Bounded by the four planes of, right, x equals 0, y equals 0, z equals 0. This is y, z plane, x, z plane, x, y plane. And x plus y plus z equals 4. So E is the region bounded by these three. As you can see in the picture, that would be x, y, z. X, y, z intercept is 1, 1. Okay? This tetrahedron region, solid. So we can consider this one as, this is our D, as a type 1, exactly like this. Okay? Projection onto the xy plane is this triangular region. This is our D. If you draw D separately, there will be 1, 1. So that will be y equals 1 minus, right? So this is your D. D. This is, you can write this one as a type 2. How? This one runs. So your E can be written as, first of all, xy is a type 1 in 2D. X given 0 to 1. For given x, your lower curve is y equals 0. Y runs from 0 to 1 minus x. For given xy, your bottom surface is z equals 0, right? So this is z equals 0, and then you're going up and then getting out of region through z equals 1 minus x minus y. This forms upper surface, u2 of xy, right? So z runs from 0 to 1 minus x minus x. That would be the analysis of the region. Just like double integral, iterated integral, as long as you analyze your domain as a type 1 or 2 or 3, then you can just copy it down here in the iterated integral. Okay? So, therefore, this function z in triple integral over e will be just following this. X runs from 0 to 1, y runs from 0 to 1 minus x, z runs to 1 minus x minus y, function z, dz, dy, and dx. Alright? So, from the inner integral toward outwards, right? So this is from 0 to 1, 0 to 1 minus x, 1/2 of z squared. Now, z runs from 0 to 1 minus x, right? dy, dx. To make it clear, I just wanted to write z, because just in case you have a, z and x and y, everything shows up, then it would be helpful to say for which variable we're substituting. Okay? So this is 0 to 1 minus x, 1/2, 1 minus x minus y squared, z0 squared is 0. So you have to do this. Now you don't have to break up this one. U equals 1 minus x minus y. This is negative of 2 and 3, 1/2, 1/3, 1 minus x minus y to the third power. Now this one, y, this one is quite helpful to write this way, so that you don't put this into x mistakenly. Then dx. Alright? So what do you get? Minus 1 over 6, plugging in y equals 1 minus x minus parenthesis 1 minus x will be 0. 0 to the third. Minus y equals 0. 1 minus x to the third power. Minus minus cancel. 1 minus x to the third power. Minus, so you need 1 over u. 1 minus x to the fourth power. So minus, because u equals 1 minus, it will be du equals minus, dx equals minus du. 1/4, 1 minus x to the fourth power, 0 to 1, negative 1 over 24, plugging 1, 0, 0, 1, 1 over 24. Okay? So, that was the first example. The second example, no, that was example 2. That's the first example of actual triple integral evaluated using iterated integral through the analysis of the domain in particular type. Okay? Now, example 3. Again, evaluate in triple integral of another simple function z again, where z is bounded by what? Z plus 2x squared plus 2y squared, and z equals 8. Now this is parabola, right? Z equals 2 times r squared. X squared plus y squared equals r squared. So r is the distance from the origin to the x point xy, right? R is, so r squared. As you go away from the origin, your z coordinate rises to r squared, parabolic way. So it's parabolic. So the okay. This is the projection onto the xy plane. This time is z equals 8. All right? So, if you solve this one together, so x squared plus y squared equals 4. So this is circle with radius 2, right? In the xy plane. So your d is this, okay? This is your d. Projection onto the xy plane. This is d. D can be written as in the domain, well, I can use, in polar coordinate, right? And then your E will be, x, y, z, where for given x, y in D, z runs from where? For given x, y, you enter through this plane, this surface, 2x squared plus 2y squared. And then through this point, we go out. That is through this. This is your lower surface through the region. This is the upper surface. So z runs from two x squared plus 2y squared through 8. Okay? So, your triple integral can be written as, right, first of all, for given xy, z runs from 2x squared plus 2y squared to 8 dz. And this is double integral, okay? I'm not going to analyze D as a type 1 or type 2 in xy plane, because I plan to use actually polar coordinates in this double integral after you do z integral. Okay? So what do you get? This is 1/2 of z squared, right? Z squared from dA, so you will get 1/2 864 minus this one. This is 2 times x squared plus y squared. 2 squared. 4 minus x squared plus y squared squared. Okay? Now, we want to write this one as a polar coordinate double integral. Then d can be written as 0 to 2. R runs from 0 to 2. Theta runs from 2 pi. 1/2 copied. 64 minus 4 r squared squared. Right? This is r squared. X squared plus y squared is r squared squared. The entire integral times r dr d theta. Okay? So you're going to have what? You're going to have 0 to 2 pi, 64r minus 4r to the fourth. Now, fourth r fifth d theta. And you can finish easy. All right? R equals, oh, r should be over here. Sorry. 2 theta. R has to be here. Theta has to be over here. Sorry. Okay? And this one you can easily finish, right? This is easy. Integration with respect to r times just 2 theta. Okay? All right. So you can finish this one easily. Take a look at your general 256 pi over 3. Now, application of triple integral. First of all, a volume application of triple integral. Okay. First of all, volume. Okay. Now, if your integral function is constant function 1 in the domain E, in E or on E, I don't know, then what do you have? F of x, y, z. Oops. So, 1 dv. Do you remember? The original definition of triple Riemann sum is limit of L and n goes to infinity. Triple Riemann sum, I runs from 1 to L, J runs from 1 to n, K runs from 1 to n. Function f of x, I, j, k, y, I, j, k star, z, I, j, k star times delta v, right? You split the domain into small, soft, rectangular box. Each rectangular box volume times the function value at one of the sample points inside the sub-rectangular box. But when your function is constant 1, this is 1. You're adding the volume of each sub-rectangular box. That will be always 1. The entire volume of the region, isn't it? Right? So, triple integral of a constant function 1 over region E give you volume of E. So this is very similar to this. Double integral of a constant function 1 will give you area of V. Alright? The same idea, just the one more dimension. Now, mass and moments. You don't have to do moments, actually. Maybe center of mass. Okay, so here, mass and moments. So let's say you have a solid. Some solid. For any given x, y, z, there is mass density, rho of x, y, z, like gram per cubic centimeter or kilogram per cubic meter, and so forth. So how much of mass per unit volume you have? For example, a pure water will be 1 gram per cubic centimeter. Okay? Pure gold will be about 19.2 gram, 19 point something gram per cubic centimeter. All right. So if you're given somehow mass density function for every point in the region, in the solver, then you can calculate the entire mass of the body. Now, normally, when you have a constant mass density, then you have this is total mass over volume. So mass equals constant mass density times volume. That's when you have a constant mass density. But what if your mass density is changing? Different composition in different parts of the body. Then rho of xyz may not be constant function. It could be, varying function of xyz. In that case, what do? You want to split entire region's small sub-rectangular boxes, and some small rectangular boxes, you do this. Delta M will be rho of xij k. A sample point within that box times delta V will give you mass of that small rectangular box. And you add them up for ijk. That would be a very good approximation of entire mass by calculating small rectangular box's mass at a time. Okay? Because it is so small, we can assume that your mass density is almost constant over that small ijk sub-rectangular box, right? So over there, just approximate constant value of the mass density times volume of that sub-rectangular box will be mass in the ijk sub-box. We add them up. That's going to be total mass approximate value. If you want to get exact value, you have to take limit. That's precisely triple integral. Limit of triple Riemann sum. That is triple integral of mass density function with respect to volume. That will give you total mass. Okay, this is the total mass. Now, center of, well, I'm not going to explain, so I'm going to just give you this. The moments about the three coordinate planes, let's say, in this textbook they call it m sub y z. So just x times rho of x, y, z, rho of x, y, z, dv, m sub x is equals the y against rho of x, y, z, dv, z against rho of x, y, z, dv, and then the center of mass. Center of mass will be this value over total mass m. Total mass m. So y, right? I will try with this. Yeah. X rho of x, y, z. This name is really bad. I don't like the name in the textbook. I will just remember this way. Okay? This was just rho of x, y, z triple integral. This one is x times rho of x, y, z triple integral. This time y times rho x y z triplet roll over capital N. Finally, z rho x y z triplet 0 over M. Okay, that would be center mass. Sometimes we write x bar, y bar, z bar. Okay, now you don't have to worry about moment of inertia. It takes a lot of time to understand what moment of inertia is, so I'm going to skip this. If you take 2532, 2-unit version, then we will cover this, but in 2533, we just don't have enough time to go through all these applications. So center mass, up to center mass, you have to understand, but not moment of inertia, so don't worry about it. Okay, now let's do, I have to check video recording from time to time. Let me check. All right, now example 4. Find the volume of the solid E bounded by elliptic cylinder bounded by elliptic cylinder, 4x squared, z squared equals 4. If I write it again, you can write it this way. Z squared over 4. Okay? You can write it. So, and then the plane y equals 0 and y equals z plus 2. Y equals z plus 2 is, if you draw it this way, you can write it z equals y minus 2, right? If you consider z as like y axis, y is like x axis, you're going like this. Okay, negative 2 and 2. This is the line. Now, this is not a line. This is a plane in xyz space. So, now x-axis is going towards you, out of the plane. X, y, and z. And this is the plane perpendicular to the yz plane, parallel to the x-axis. Okay? And this one is xz. It's an elliptic, right? This is an elliptic cylinder with the along z is longer. So it'll be going like this, all right? Z. This will be 2, and along x is 1. This is negative 1. This is negative x-axis going that direction. Okay? This is negative 1 and 1. And then, so it is elliptic cylinder along the direction of y. And then you're cutting, and this one going through this, going this way, perpendicular to the yz plane, right? So it'll be going like this. And going out of here. Okay? So there was a better way we cut it this way. Okay? So, thinner. So this is when I y equals 2 here, right? Y equals 2. So this solid. Okay? So now, so we have to consider this one is a type 2 in 3D. Projection of the region onto the XZ plane is, ellipse over here. So this is D. Okay, this is D. And then the U1 of XZ will be y equals 0. This one is y equals z plus 2. So for given x, y, you're going getting out of here, right? Through this plane. Entering the region through y equals 0. Okay? So your D is actually, if I draw D, region D is x-axis, y-axis, no, z-axis. I want to write this one as x runs from -1 to 1, z runs from here to here. Okay? And what do you have to do? Okay? You have to solve for z. Z squared equals 4 minus 4x squared. Z equals square root of 4 minus 4x squared plus minus. So the upper one, upper semi-ellipse will be z equals square root of 4 minus 4x squared. Lower semi-ellipse will be z equals negative of square root of 4 minus x squared. Okay? So you can write D is on the xz plane, x runs -1 to 1, okay? X runs from -1 to 1, and z runs from here, negative of this one to positive that one. For that xz, E is it type 3? Is it called type 3 or type 2? Oh, this is called type 3. I'm sorry. Yeah. Type 2 is onto the YZ. Okay. This is X, Y, Z. We're given X is Z in the D. Y runs from 0 to z plus 2. Okay? So you can set. Okay? So your volume is, they ask you to find the volume. Triple integral of constant function 1 over E. So according to this, x from -1 to 1, and z runs from here and y runs from 0 to z plus 2 of 1 dy and then dz dx. Okay? So you get what? -1 to 1 This one is y2 from, what is it? Constant function 1 from 0 to this is z plus 2 minus 0. So z plus 2. Now, with respect to z, this is an odd function. See, when f is odd function, that means i.e. f of negative x equals negative of f of x, or y equals f of x has origin symmetry. You know, like this. Origin symmetry. You have the same shape, but one is up, one is down. Then minus a to symmetry interval around origin. From minus a to a, f of x dx will be 0, right? For z, this is odd function. Odd function. From minus something to positive something. So that integral will be 0. So I'm going to write it. Minus of 4 minus 4x squared z dz plus, I'm going to split over addition, 2 dx. And this one will be 0. And this one is 2 times this minus this. 2 times this, 2, so 4. This is what you're going to get. Okay? Now, this one is actually, this one is 4 times 1 minus x squared. So square root of 4 is 2. So 8 minus 1 to 1. 1 minus x squared dx. This is an even function. Or, doesn't matter. Now, you can use these. You see that? If you really want to calculate this one, you have to use substitution, trig substitution, x equals sine theta. But I don't have to do that because this one is a semicircle with, it's a unit circle. All right? When you have a unit circle like this, y equals plus minus square root of 1 minus x squared. It's an upper semicircle from minus 1 to 1. It's just half times pi r squared. Radius, the area of this semicircle, 1/2 of pi r squared. R equals 1. So it is 4 pi. Okay? Now, you remember that, you know that this one is 2z. Right? That's why this one minus 2 times square root of 4 minus 4x squared. Another 2, that's why you got 4. Okay. So that was type 3. Finding volume means triple integral of constant function 1 over the region. Now, final example 5 is actually from page 881, number 34. All right? I chose a problem in the exercise as our last example of this section. Example 5. Sketch the solid over which the following triple integral is evaluated. Then rewrite the integral as an equivalent in iterated integrals as type 1 solid. Okay? So your iterated integral is given this way, 0 to 1. 0 to 1 minus x. Some function. They didn't tell you what f of x, y, z is. Now they ask you to write it as what? Type 1. Okay? dz, dx, dy, or dz, dy, dx. One of those. This is type 1 in 3D, right? We want to write in one of those. So we have to change the order. In order to do that, we have to recognize this one as a triple integral over a certain region. E. We have to recognize the shape of E from here. So this one must be triple integral of over E, where your E can be written this way. What is it? For given x, z runs this, and then for given x, z, y runs. So given x, z, y runs something that is type 3. It is given as type 3, right? Now let's recognize the shape. So the domain D, this one covers domain D. D is x and z run 0 to 1, 1 minus x squared. Part of parabola. 1 minus x squared. X runs from 0 to 1, 0 to this. So this is your D. The x is z plane. Now, so then your D can be written this way, right? From z 1 to 1, right? This is your D on the x z plane. X z plane. Y runs from y equals 0 to y equals 1 minus. Okay. Y equals 1 minus x means this 1, 1. It's a plane, right? Perpendicular to the xy plane. So if you draw it, xy, perpendicular to the xy plane, all right, through 1 and 1, right? So you have an x and y, 1 and 1. Y runs from y equals 0, means x is equal, all the way to this. So that means from actually circular, not circular cylinder, this is parabolic, this cylinder, you are cutting this way. So, can you see this? So this is, you can think of this one as this is parallel to the y-axis. You're cutting this way. Okay? So y runs through y equals 0 to y equals 1 minus x. We're given here and going all the way to here. Right? Now, we want to analyze this one as type 1, 3D type 1. That means your domain should be on the xy plane. Hey, this can be our D, right? Our D xy plane. Okay, so this is our D in xy plane. All right, that is easy. X is between 0 and 1, y between 0 to 1 minus x, right? And then z runs what? Z equals 0 to this one. What is it? Z equals 1 minus x. What's it? That's the upper. This is the upper surface. Z equals 0 will be your lower surface when you consider this one is along the z direction, type 1. So E can be written as dxy, which is x runs from 0 to 1, y runs from 0 to 1 minus x. It's domain on the xy plane. For given x subject to d, z runs from 0 to 1 minus x squared. You can write it this way, all right? Then you just have to write it twice. Therefore, E can be written as, okay, dy dx, x runs from 0 to 1, y runs from 0 to 1 minus x, z runs from 0 to 1 minus x squared. Now this one can be written as y runs from 0 to 1, x runs, for given y, x runs, x equals 1 minus. You can write it that way too, as a type 2 into v. 1 minus y, right? 1 minus y. Then you can write it 1 minus y for given y and dx. Okay? Either this way or this way. Okay? So you will have another problem. This is actually harder than you think. Maybe already you think this is hard. Because you have to recognize the shape, three-dimensional shape, through analyze iterate integral. So write it down as the description of solid. So this is the opposite process what we have been doing. Usually you are given the description of the solid and you write the triple integral accordingly as iterated integral. This is opposite process. And then after you figure out the solid, and then you rewrite it as a type 2 different type. So the challenge of chapter 12 is, especially this triple integral, involves understanding three-dimensional solid in your mind through the description. This is one of the biggest challenges in Calculus 3. You have to visualize three-dimensional solid with the help of this description, type 1, type 2, type 3. Okay? Nobody can do this one naturally right away. Everybody has to go through practice, a lot of practice. Through good examples you go through, and then you have to do practice homework problems. Now, I already uploaded all the solutions, right? For you to study with. Okay? All right, so this is the end of part 2 of section 12.7. So we finished chapter 12.7, okay? This is the first part of the lecture of Monday, April 6th, I guess, right? Today is April 5th. Yeah. So I'm recording April 5th, but this is for the class of April 6th, Monday. All right? All right. Well, thank you, and I'll see you next time.